at the most. So it's smaller or equal to 3,000, okay? And what we are not saying here is, but it makes sense, is that we are only allowed to buy non-negative amounts of each beer. Okay? So, yeah, I mean, it's... now let me think. Is this really correct? Is that really correct? So I buy 4 liters of light.
Nie, no to čiernym to bolo len ako možné.
No čiže 0 až 2 litre čierneho.
Áno.
No ale koľko môžem kúpiť čierneho, keď som kúpil 4 biele? No čiže 0 až 2.
0 až 2, okay, so let me translate it. Okay, so this, let's look at this constraint. Let's imagine XL optimum is 4. Okay, so what we are saying is XD is less than 8. Which means I can buy 7. But that conflicts with that one. So this constraint is not correct. So how can we fix that? So you see, these are trivial example. Trivial example, but we have to be careful. Because if we are not, we solve a different problem. So how should the constraint read? Okay. So let's imagine I have XL equal to 4. Which constraints do I need? 2xd less than XL. That's the constraint that we need. Okay? So little details. Okay? So it's that constraint. Okay? So be careful. And again, these are trivial example. Okay? In practice, we have tens of thousands of variables and hundreds of thousands of constraints. It takes really an effort just to formulate the problem correctly. Okay? Just imagine you make a mistake and suddenly you get a solution and you wonder. I mean, in the better case, your company loses money. In the worst case, your company explodes because there will be, imagine you are determining the operating temperatures for your reactor, and you mess up with the constraint, and suddenly it says, let's set the temperature to 10,000 degrees. I mean, it's optimal solution for this problem, but your company will soon stop to exist. Okay, so be careful. Okay, so for the remainder of the lecture, I will consider another economic linear program, which is formulated like this. And I would actually now come to the point which Jano has made, like, what if I change this objective function here? I mean, would I get the same solution? Would I get a different solution? Actually, and now probably you will see why I have asked you to always to draw a constraint and so on. So let us draw these constraints here. Okay? So obviously these non-negative constraints are just this constraint and that one. Okay? And then we can plot also the remainder of the constraints. What we see here is that this blue shape, that denotes the space which satisfies constraints. So our optimal solution has to lie in this space, nowhere else, because otherwise it would violate constraint. Now the question is, where is the optimal point? Well, we don't know until we know the objective function. Okay, so let's draw the objective function as well. And it's this one. And actually, since we are maximizing, we can push it in this direction. So actually, we are trying to push the objective function as far as we can, such that this line still at least touches one point of the solution space. This blue area is called the feasible set. So that's the set of all optimization variables which satisfy constraints. So obviously, the optimal point is here. But now imagine what happens if we rotate this objective function like this. So we would only be maximizing x2. Okay? Then the optimal point would suddenly change here. what if we would like to maximize in this direction? Okay? Then the optimal point would be either here or there, because actually this whole line segment would be optimal point. Okay? So, sorry? Well, I said if we maximize in this direction, which is the same as minimizing x1. Okay. Okay. So if we change the objective function, we could also change the optimal solution. Okay. So you cannot arbitrarily change the objective function because your solution can change. Okay? Second point: these circles here, they are the vertices of this blue set here, of this feasible set. Clearly, the optimal solution of a linear program is at one of these vertices. In other words, there is a naive way of solving linear programming problems. Draw this shape, find out what the vertices are, at each vertex evaluate the cost function, and simply take the vertex which has the largest value of the objective function. The problem is the number of vertices is roughly 2 to the power of the optimization space. And now recall that I said linear programming problems usually have those practically relevant ones. Hundreds, thousands, 10,000 optimization variables. 10 to the power of 100 is a large number. Okay, that's again the number of atoms, roughly. In other words, this naive way of investigating the value function at each vertex of this feasible set is not used in practice. This is a three-dimensional example. So here we see that we have really many, many vertices. And what we are going to cover is the simplex method, which essentially how it works is that it starts at one of those vertices and it finds a good path towards the optimal point without having to even discover all possible vertices. Okay? And just one comment to the number of vertices. A good example is a box. A box in 1D is just a line segment which has 2 vertices, right? 2 to the power of 1. Box in 2D has 4 vertices, 2 to the power of 2. Cube would have 8 vertices, that's 2 to the power of 3. Now imagine 100 variables in this cubic space, and we have 2 to the power of 100 vertices. So there is no way to explore all of them. However, there is a clever algorithm which basically only looks at selected vertices. And here we come to the relation to the Karush-Kuhn-Tucker method. Essentially what the simplex method does it avoids exploring all possible combinations. It starts with one combination and it finds what is the next one to look at, which is most likely to be the optimal one. If it is not the optimal one, it again finds the next one, which is the most likely to be the optimal solution. So the simplex method is about exploring this path and finding the optimal solution without having to explore all possible combinations. And this so-called simplex method was discovered or developed by George Dantzig. Actually, this is probably the most important person in the field of optimization in the 20th century. We could roughly say that this guy has won the Second World War. Essentially, he was working for the US Army, and they were looking at how to cause maximal damage to the Germans with minimal expenditures while satisfying constraints. And these constraints could have been transportation constraints, they could have been production constraints, and so on. Basically, they were looking at quite large problems, hundreds of optimization variables, thousands of constraints. We know that's 2 to the power of 1,000 combinations to explore. If they would do it manually, even on their primitive computers, probably they would still be computing the optimal solution and the war would be lost for them. Okay? So what this guy did was he developed the simplex method as a more effective way of solving linear programming problems, which allow them to come up with the optimal allocation of sources and productions and military attacks to defeat the Germans. And with these algorithms, they were able to compute those optimal solutions in short time frame. Okay? So this guy is really important. Everybody depends on this guy. Linear programming, I mean, he has done this during Second World War, so the whole area of linear programming, I mean, that dates back to the 1940s. Okay, so it's pretty mature field, 70 years old. Okay? So this is the guy, remember him. And what he did was he developed the simplex method, which can solve arbitrary linear programming problems. However, it requires a special input form. It requires that we solve the problem of maximizing linear functions subject to equality constraints and subject to non-negativity constraints. So what George Dantzig said is, this is the algorithm. If you want to solve this problem, I can do that. However, not all problems are immediately in this form. What we have seen here, we have no equality constraints. So the question remains, how to transfer a problem like this into this standard form. And there are 3 steps. Remember them really well. They are used almost everywhere. Okay? So let us note what are the differences between these 2 problems. Where the first immediate difference is that here we have equality constraints, here we don't have equality constraints. The second difference, which is less obvious, is that in this problem, the optimal x can also contain negative values. However, in the problem on the right, these can only be non-negative. So the question is how to kind of create the correspondence between negative x's and positive z's here. And the transformation, therefore, proceeds in 2 main steps. The first main step is that we convert these inequality constraints into the corresponding equalities. And this is probably what you have covered in the second year class on optimization. So how we achieve that is that to the left-hand side of the inequalities, we add so-called slack variables, which are non-negative. Essentially, what these slack variables denote is what is the distance of x from corresponding constraints. And then we let the optimization to determine what is the kind of the optimal distance such that when we shift the point, it ends up exactly at the equality constraint. Okay? So we add as many slack variables as we have constraints in our original problem. So remember, we started with this formulation. We have only x's as the optimization variables. To convert the problem into this form, we also need to introduce as many slack as there are inequalities, meaning we have larger dimension of the optimization space now. But we are not done yet. We have just eliminated the inequalities and converted them into equalities. What we need to do next is to deal with the fact that x can be both positive as well as negative. And to deal with this, what we note is that any number, being positive or negative, can be written as a difference of 2 positive numbers. So minus 2 can be written as a difference of 1 and 3. 1 minus 3 is exactly minus 2. Okay? So let us introduce additional optimization variables, x plus and x minus, both of them being non-negative. And then we will use this line here as a substitution everywhere where we see x. Meaning, we see x here, so we plug in this substitution instead of x, and we obtain exactly this. What we also need to do, however, is we have to substitute for x in the objective function. So instead of x, we put x plus minus x minus. However, this standard form, the Dantzig form, expects maximization. But we can easily convert minimization to maximization just by maximizing minus the quantity. Okay? So these 3 steps are really frequent. used almost everywhere, and they are used to convert this standard form into this one. It's also very easy to convert in the opposite direction, and that you can do as a homework. Okay? So bottom line is, any linear program in this form can be equivalently represented as a linear program in this form here. So they are really the same problem. They are just formulated differently. And to see that, note that we have now x plus x minus and the slacks as new optimization variables. So to have equivalence between this formulation and the formulation on the right, what we need to do is that when we multiply this vector of optimization variables by some other vector, we must recover exactly C transpose times x. Okay? And we do that by multiplying x plus by minus C and x minus by plus C. The minus here is because we have also converted minimization to maximization. Okay? So after the expansion, this is exactly equal to minus C transpose x. And here, notice that what we get is a times x plus minus a times x minus, which is exactly a times x, plus identity matrix times S is equal to B. So that's exactly what the inequality constraint is, converted to equalities by using slack variables. And all constraints here are non-negative. So let me give you kind of an example of how that works. So you can look at the bottom part, but I would rather that you know how to convert the stuff. So we would like to maximize 4x1 plus 6x2 subject to minus x1 plus x2 less than 11, x1 plus x2 less than 27, 2x2 plus 5x2 less than 90, and x1 and x2 being non-negative. So what we see here is that what makes a difference from the standard Danzig form is that we have inequalities and we have to eliminate them. We have to convert them into equalities. We don't have to do anything else because we already are doing maximization and we already have non-negativity constraints. Yeah? Sorry?
Third constraint.
2x1, yeah, here. Thank you. Right, yeah. Okay, so what we do is, and I will do it by the help of the whiteboard like this. So this is the right-hand side. Okay. So to convert this inequality into equality, what we need to do is to add a slack variable. So we add a slack variable S1. We add it here because we know that the slack must be non-negative. And what it does, it converts this inequality into an equality. We do the same here. We add S2 that converts inequality into equality under the condition that S2 is non-negative. And the same here, plus S3 converts it into equality, and S3 must be non-negative. And in my, in the result, this is S1, S2, and S3. Okay? So that's how the problem is converted into the standard form. Now, why we are doing that? Because now we are going to form something which is called the simplex tableau. So a simplex tableau consists of individual rows. Each of those rows represents one of these equality constraints, and the final row represents the cost function. So let us see whether there is some relation. Essentially, what we see in the first row is that they are exactly the leading coefficients of individual decision variables in the left-hand side of the equality. And the final column here is the right-hand side of the constraints. Okay? Then we repeat that for the second constraint. So that's 1x1, 1x2, plus 1 times x4 must be equal to 27. And this is for the final constraint. And then the final row, well, sometimes it is even the very first row, it depends on the convention, contains the negative values of the leading coefficients in the objective function. So we take the leading coefficients and we put negative sign in front of them. What we have just formed in the initial simplex tableau. In this simplex tableau, what we have is we have 5 optimization variables, and we see that we can split them in 2 groups. Those 2 groups are called basic variables and non-basic variables. Basic variables are those where there is only one non-zero entry in the corresponding column. So x3, x4, and x5 are basic variables, and the remaining variables are non-basic. Okay? So remember how to form the simplex tableau and how to classify the variables into basic and non-basic one. Needless to say, the exam that you will have for the next exercise will verify whether you have really remembered how to do that. So the initial simplex tableau, and we are doing the classification of the variables. Now what we do is that we obtain the initial vertex in our solution space. Remember, have that picture in mind. What the simplex method does is it starts with initial vertex and then assembles a clever path along the vertices. So now we are going to find the first initial vertex. How do we find it? Well, what Mr. Danzig said was set the free variables, meaning the non-basic variables, to 0. So our non-basic variables are x1 and x2. Set them to 0. And set the basic variables, x3, x4, and x5, to the corresponding right-hand side. Why do we do that? Because then all constraints would hold. Okay? So what we are saying is set x1 and x2 to 0, and then set x3 to 11, x4 to 27, x5 to 90. So essentially what we are saying is this goes away, and with the setting x3, x4, x5 as here, the constraints are satisfied. And by this we have found the initial vertex, a point which satisfies all constraints, but is not necessarily optimal. How do we know it is not optimal? Well, there is a rule for that, but we can also see what is the objective value for this initial vertex. What is the objective value if we assume this setting of optimization variables? That's just 0, because it's 4 times x1 plus 6 times x2. Okay? Here is the cell which will contain the current value of the objective function. Currently it's 0. Okay? Now we start to do magic. What we do is we ask questions. We ask the following question first. Okay, so obviously to maximize this objective function, I should change x1 or x2. Now, which of them should I change such that I am more likely to increase the value of the objective function? With respect to which variable is the problem more sensitive? Is it more sensitive with respect to x1 or with respect to x2? With x2, because we have higher leading coefficient in the absolute value. Okay? So we see that x2 is the variable which influences the cost function more than x1. And we see that based on this leading coefficient. Okay? But we have to be careful. Okay, so we say, I can gain more profit by increasing x2, but I cannot increase x2 as much as I wish because I have constraints. So I have to ask a second question. Which constraint will be violated first if I start increasing x2? That's the question now. So imagine you are increasing the value of x2. Which of these constraints you would violate first? You can also think of them as inequalities, okay? Remove x3, x4, x5 and put inequalities back. Which of the constraints would be violated first? Say I set x2 equal to 10. Will the first constraint be violated? The first constraint would mean x2 is less than 11. That constraint will be satisfied. x2 less than 27. Even that one would be satisfied. But the last one is, well, 5 times 10 that's 50, that's still satisfied. Okay, so I can set x2 to 10, but I'm looking at like what is the highest possible value that x2 can have. So let's say I set x2 equal to 20. Okay, then this constraint would be violated. This one would be satisfied, and this one would be violated because we have 5 times 20 is 100. Okay, so now we have two candidates. Which of them will be violated first by increasing x2? Actually, the one which has the lowest ratio between this right-hand side and this leading coefficient. Okay, so the ratio here is what's 90 divided by 5? 20 times, not even 25, 16. That's 16. Am I right? Yeah, that's 16. And the ratio here is just 11. Okay. So we are looking at the constraint which has the lowest ratio between the right-hand side and the corresponding leading coefficient. Okay, so the ratio here is 11, here it's 27, and here it's 16. So we see that it's the first constraint which will be violated first by increasing x2. Okay? And by these two arrows, we have now identified an important point. We have identified that we will make x2 a new basic variable. Now, what makes a variable basic? That it has 1 here, and in all remaining columns, it has just zeros. Okay? So the next step that we are doing is we are using elementary row operations to achieve that this coefficient is 1, and here we have all zeros. Now, what does it mean, elementary row operation? We take this row as fixed, and we add some multiplies of this row to the remainder of the rows. Okay? But this is probably what you have already covered in the basic optimization course, right? So remember what we need to do is we have to keep 1 here and get zeros here. So how can we get 0 here is that we subtract from this row minus 1 times the first row. Okay? What do we obtain is here we have minus 1, and we are subtracting the minus 1 of this row. So minus 1 times minus 1 is plus 1. And here we would get a 2. Okay? Here we would get 0, and here these constraints would be modified accordingly. Then we need to get a 0 here. How can we get a 0 there? And subtract that. So we are adding minus 5 of the multiple of the first row to this one. Okay, minus 5 times the first row. When we do that, this would be plus 5. So here we would get 7. This is minus 5 plus 0. That would be minus 5, and so on and so forth. All the way also here to the right-hand side. So that gives this row. And actually, we have to also do the same for the final part. So here we have to add 6 times the multiple of the first row, right, to get 0 here. So we do that, and we obtain this one. The operation that we have just done is technically called pivoting. So pivoting is a series of elementary row operations until in the selected column we essentially get a new basic variable, which means we have leading one in the column, and then the remainder of the entries are just 0. Now, why did we do this? Because now we have obtained a new basic variable. Suddenly, x2, which was previously a free variable, is now a basic variable. We know that because it has all 0 entries and just one non-zero entry. However, some variable which before was a basic one, that was x3, now is non-basic variable. Okay? So we have obtained a new vertex. How do we know the coordinate of the vertex? Well, we apply the same procedure. We set the free variables to 0. The free variables are x1 and x3. And the basic variables, we set them to the right-hand side of the constraint. Now, what we can see here is that, obviously, all constraints are satisfied again. So x1 and x3 is 0. So we must have x2 equal 11, which which is satisfied. Okay? The second one says x1 0, x2 plus x4, 11 plus 16 must be 27, satisfied. We have 2 times x1, x1 is 0, 5 times x2, so 55, plus x5, 35 is exactly 90. Okay? So what we have done by this pivoting operation is we have found a new point in the solution space, which is characterized by x1 being equal to 0, x2 equal to 11. What is the value of the objective function for these settings? 66. 4 times x1 plus 6 times x2. Interestingly, it's also the number that we have obtained in this final cell after all those elementary operations. So those pivoting operations, they always kind of keep the value function as the entry in the final cell. Now we have to ask ourselves, is this the optimal solution or not? And actually, what Mr. Dantzing is that he has proven that the solution is only optimal when the final row in these columns, which correspond to individual variables, if it only contains entries which are positive, meaning if the last row contains a negative value, then this solution is not optimal. And we have to iterate further. So that's exactly what we do. We again ask those two basic questions. Increasing which variable will influence the objective function more? Would it be x1 or x3? Clearly x1, because x3 is not even included in the objective function, right? So we will increase x1. The question is, increasing x1 can violate constraints. Which constraint will be violated first by increasing x1? Again, the argument was, look at the ratio b divided by the corresponding value and look for the smallest positive ratio. Now, why positive? Because essentially this says, if I increase x1, I actually go farther away from the constraint. The constraint is x1 less than 11. Okay, so if I have minus x1 and I increase x1, I actually go away from the constraint into safety. Okay? So that's why we are only looking at positive ratios between the right-hand side and the coefficient. So we don't even have to consider the first constraint as dangerous, because by increasing x1, we will not violate it. But we could violate either the second or the third constraint. Which constraint will be violated first? So the ratio here is 8, and the ratio here is 5. Which of them is smaller? That's the one which will be violated the first. Okay? So it's this row, which is kind of dangerous by increasing x1. And this gives us a new so-called pivoting variable. So now what we would do is we will apply pivoting operations such that this element is 1, all other elements are 0, such that we make the variable a basic variable, and some other variable will become a free variable. Okay? So tell me, which elementary row operations should we do to achieve 1 here and zeros there?
Divide the whole row by 7.
That would be the operation performed here. Okay, what would be the operation here? By 1 over 7 and add it here. Okay, so we take 1 over 7 multiple of this row and we add it to the first row. Okay, what that will do is it will zero out this component. This one will keep intact because we have 0 in there. Here we will have 1 minus 5 over 7. Here we would have 0 that stays. Here we would have 1 over 7. And here we would have 11 plus 1 over 7 times 35. 1 over 7 times 35 is just 5, so here we would get 16, right? So we would get exactly this row. And now we have to do it for the second one. So by which coefficient do we need to multiply the third row such that we end up with a 0 in this element? So again, we look at the ratio of these two coefficients, and if the ratio is positive, we have to make it actually negative because we are always adding. Okay? So we do minus 2 over 7, the multiple of the third row. That will convert the tableau into this form. We have to convert also the final row. Okay, so again, we look at the ratio here, and since the ratio is negative, we again make a negative of that, so we are adding 10 over 7, the multiple of the third row. And for the third row, we do as Tomáš has suggested, we just divide by 7, the whole row. Okay? And we have a new tableau. And in this new tableau, we have a new classification of variables. So we see that we now have x1, x2, and x4 as the basic variables. How do we see that? Well, because in each row, there is just one non-zero entry for corresponding variables. And the remainder of the variables are free. Now, if somebody tells you, this is the tableau, this is the classification, what is the feasible solution? What is the value of x1, x2, x3, x4, and x5 which satisfy constraints? So remember, free variables, we set them to 0. Basic variables take the values of the corresponding right-hand sides. So x2 would be 16, x4 would be 6, and x1 would be 5. For the free variables, x3 and x5, they would be 0. Okay, so that's essentially this one. The value of the objective function, if you don't trust Mr. Danzig, you could compute again from the cost function. So that's 4 times 5 is 20 plus 6 times 6, that's 36. Sorry, no, this one, 6 times 16, so that's 60, 96 plus 20, so that's 116. Which is, strangely enough, exactly the entry that we have obtained by elementary row operations. Okay. Is this the optimal solution? If somebody gives you this table and asks you, is this the optimal solution? I mean, this is the solution, right? Is this the maximal profit that we can achieve? No, why not? Because we still have a negative value in the final row. And we repeat this until we converge to just positive values. Okay? So again, same question. Which variable should we increase as to maximize the value of the objective function? Well, none of them really appears here, so we have to choose the one which has the smallest negative coefficient here, because only those negative coefficients can influence the function value. Okay, which constraint will be violated first if we start increasing x3? Now it's less obvious, right? So let's do those ratios. So the first ratio is 16 over 2 over 7. The next one is 6 over 3 over 7, and actually the last one we don't have to consider because it has a negative leading entry here, which essentially means if we increase x3, we go into safety. Okay, so we only need to consider entries which have positive coefficients. And among those positive ratios, we have to identify the one which is smallest. Okay, so this is 42 over 3. And this one is 112 over 2. Okay, so obviously this one is lower. Okay, so it would be actually the second constraint, which is most dangerous by increasing x3, and we do the same. Actually, this pivoting that can be nicely automated, and that's what the solvers are actually doing inside. So how do we get 1 here, 0 there, 0 there, and 0 there? Well, elementary row operations, okay? Here, just since we have the fractions, it's kind of more involved. But again, we just need to make the ratio of these two numbers, okay? So even though there are over 7s, they cancel out, so the ratio is really just 2/3. And we add that. We add the 2/3 multiple of the second row to the first row, and we obtain these results. Here, again, the ratio between these two, that's 5/3. Here, the ratio is over 3. And what we do here is we just multiply by 7/3 to convert this encircled value into 1. Okay? Right. And again, classification. Okay? Basic variables are those which have just one non-zero entry in the corresponding column. The remainder are free variables. Feasible solution is such that we set the free variables to 0 and the basic variables to the corresponding right-hand side. And we can easily check that all constraints are satisfied, and this is the objective value, 132. So if you remember, we started from 0, then went to 66, then to 116. Now we are at 132. The question is, can we achieve even higher profit? No, because all entries in the final row are positive. Okay? So here is where the algorithm terminates and says, this is the optimal value. Okay? Now, let me show what the algorithm really did graphically. Okay? Now, if you remember, the very first solution that we obtained was x1, 0, x2, 0. The next one was x1, 0, x2, 11, for which the function value was 66. The next solution was 5 and 16. That was that 116 value function. And then this was the solution at the final iteration with the function value of 132. And if you remember, the cost function really went in this direction, so this was really the optimal solution. So here we see what the simplex algorithm was doing. It was finding a first vertex in the solution space, and then it was iterating as to find a path along the vertices until finding the optimal solution. And here you might argue, why didn't the algorithm choose this path? I mean, it would be simpler. It would only be essentially, here it was one pivot operation and then another pivot operation, so 2 instead of 1, 2, 3. Okay? But that's how the algorithm works. I mean, the algorithm, the simplex algorithm, is what we call the heuristics. It says, this is a good set of rules which appears to work well in practice. Remember, those rules were, look at the entry where the coefficient is the largest. Look at the row where the ratio was positive and the smallest one. If you would apply different rules, like not look at the row where the coefficient or the ratio is smallest, but the largest one, you might obtain a different path. But the point is, this is such a trivial example that it doesn't matter whether we perform 2 operations or 3 operations. That's still 0.0 seconds. If we are in a 10,000 dimensional case, where we have shape which has billions of billions vertices, then the simplex algorithm actually works really well in practice, meaning the path, it is not necessarily the shortest one, but it is also a very good practical path, which allows us to solve these problems, even though they are in huge dimensions, in rather effective time frame. There is one point to be made, and